Welcome to The Explainer. Today, we're diving into one of the most fascinating and, frankly, high-stakes standoffs in modern science. On one hand, you've got the mind-blowing, life-saving potential of medical AI. We're talking algorithms that can spot tumors faster and more accurately than human eyes. But on the other hand, there's the absolute, non-negotiable need to protect your patient privacy. So, how do we feed these incredibly data-hungry AI models the millions of medical records they actually need to learn without accidentally leaking our most sensitive personal information to the world? Well, that right there is the privacy paradox. And today, we're going to unlock it.
Okay, here's our roadmap for this explainer. First, we'll look at the AI medical dilemma. Then we'll see why anonymization fails. After that, we'll cover federated machine learning, unpack the privacy-preserving toolkit, and finally, look at the future of medical AI.
Let's jump right into Section 1, the AI medical dilemma. It really comes down to this massive tug-of-war between data utilization and data protection.
So here is the fundamental question we have to grapple with. Can AI revolutionize medicine without knowing exactly who you are? Look, we all want algorithms that can accurately predict disease and totally personalize our treatments, right? But to get there, we run headfirst into incredibly strict but totally essential privacy laws. Think HIPAA in the US or the GDPR over in Europe. These laws mandate, rightly so, that we protect personally identifiable data. But here's the catch. AI needs data to get smart. So how on earth do we balance training these life-saving algorithms with our legal right to keep our medical histories completely secret?
To really wrap our heads around the scale of this problem, let's look at the huge contrast between the tech world and the medical world. In regular tech, like the AI powering self-driving cars or mastering complex games like StarCraft, those models absolutely thrive because they're trained on massive, easily accessible open-source datasets. They literally have millions of data points to learn from. But medical AI, it's practically starving. Electronic patient records are super expensive to manage, heavily siloed inside individual hospitals and intensely regulated just to prevent unintended leaks. We simply do not have the massive global shareable datasets in medicine that we do in standard tech.
Which brings us to Section 2, why anonymization fails and the very real risk of re-identification.
Take a look at this. What's really wild here is the sheer variety of ways malicious actors can actually attack a dataset nowadays. They aren't just trying to guess a password anymore. Hackers are using sophisticated methods to infer if you're part of a dataset, or they're poisoning the AI model itself, or, and this is crazy, they're completely reconstructing patient attributes just from looking at the algorithm's outputs. The threat landscape has evolved exponentially, and honestly, our old defenses just are not keeping up.
Now you might be wondering, why don't we just delete the patient's name from the file? Well, simple anonymization is technically completely insufficient today. Let me give you a pretty scary reality check. If a hospital removes your name from a 3D CT scan of your head, hackers can use software to literally reconstruct your actual physical face right from the contours of the skull in that scan. No way, right? To stop this, doctors actually started defacing or skull stripping the images before sharing them. But doing that physically degrades the image, which means the AI gets lower quality data to learn from. And worse, if hackers do manage to crack the identity of these records, they're often sold by data mining companies to health insurance firms, who might use it to discriminate based on pre-existing conditions.
So the absolutely crucial takeaway here is that anonymization just completely fails against what experts call a linkage attack. This is a scenario where an attacker takes an anonymized medical database and cross-references it with an outside database, like a voter registry. They just match up seemingly harmless details, your age, gender, zip code, and boom, they've revealed your identity, totally bypassing standard anonymization. We clearly need a better way to handle this.
And that leads us perfectly into Section 3, Federated Machine Learning. This is all about decentralized AI. Federated learning is an absolute game changer. It's a total paradigm shift. Historically, if you wanted to train an AI, you had to gather all the sensitive data from all over the world and dump it into one giant central cloud server where the algorithm lived. Obviously, that's a privacy nightmare. But federated learning flips this entirely on its head. Step 1, we send the untrained algorithm directly to the local hospital. Step 2, the algorithm learns locally, right there on the hospital's secure computer systems using their private data. And then step 3, the algorithm returns only what it learned, the updated mathematical weights, back to the central model.
Think about how massive this is. The data literally never leaves the hospital, but the algorithm still learns. This beautifully resolves those massive data governance issues. Patients and hospitals get to retain complete sovereignty over their sensitive information because they never ever have to transmit it over the internet or hand it over to some third-party tech company. But as amazing as federated learning is, I've got to say, it's not a silver bullet, because even if the data stays locked up at the hospital, neural networks kind of act like a giant memory mechanism. They can actually accidentally memorize and leak little bits of the training data hidden deep inside those mathematical weights.
So, to fix that, we move to Section 4, the Privacy Preserving Toolkit. This is how we actually secure the data and the AI. To really pull this off safely, we need a holistic, secure ecosystem, just like you see here. Notice how it's divided up. We need secure AI to protect the algorithms themselves from being stolen or manipulated. And we also need private AI to protect the actual input and output data. We aren't just putting a lock on a door anymore. We're building an entirely secure pipeline that protects both the patient and the algorithm at the exact same time. And it does this using some truly mind-bending mathematics.
Okay, the first tool in this next-gen kit is differential privacy. Think of this as a clever way of hiding the individual in the crowd. Differential privacy essentially injects mathematical noise or randomness right into the dataset. It subtly alters the data so that an outside observer could never tell if your specific personal record was used to train the AI. But here's the genius part. The overall statistical trends remain perfectly intact. That means the algorithm still learns all the right medical lessons without ever learning your specific secrets.
Next step is a tool that honestly sounds like absolute magic: homomorphic encryption. Normally, if you encrypt data to keep it safe, you have to decrypt it before a computer can actually analyze it, right? And that creates a tiny moment of vulnerability. Well, homomorphic encryption allows the AI to do complex mathematical operations on the ciphertext without ever decrypting it. The algorithm literally calculates the result in the dark. It never needs the key to see the raw patient data. It is a massive leap forward for keeping data completely secure while it's actively being processed in the cloud.
Then we have secure multi-party computation. The researchers use a fantastic analogy for this one. Think of a secret ballot election. In an election, everyone absolutely needs to know the final joint result, but the individual votes must remain completely hidden. This cryptographic technique does exactly that. It splits up medical data among multiple different hospitals. They collaborate to compute a joint result, like training a shared AI model, but no single hospital ever sees the whole picture of the other hospital's patients. It is literally collaboration with zero loss of confidentiality.
Finally, stepping right alongside all these mathematical guarantees, we also have physical hardware-level protections. These are hardware security implementations. We're talking about specialized computer chips, secure processors, or trusted execution environments physically built right into servers and even into your mobile phone. These hardware enclaves ensure that even if a computer's operating system is completely breached by a hacker, the data processing happening inside the enclave remains physically locked down and secure right at the edge of the network. So now that we have this incredible toolkit, what actually needs to happen next to make this ultra-secure future a global reality?
Let's wrap up with Section 5, the future of medical AI and the path forward.
The experts highlight a few critical next steps to get us there. First, we really need to lower the barrier to entry for developers by creating easily accessible, open-source tools so any hospital, anywhere, can actually implement this tech. We also need deep multidisciplinary research. We've got to get the cryptographers and the medical professionals speaking the exact same language. And here's one of the most fascinating concepts being developed right now: machine unlearning. Think about it. If a patient withdraws their consent under the GDPR, exercising their right to be forgotten, how do we force a trained AI to unlearn that specific patient's data? That is a huge frontier. Ultimately, we have to create systems that are objectively trustworthy and fully auditable by regulators to build real public confidence.
So I want to leave you with this provocative thought. In an ever-evolving data economy, how will secure AI transform your private medical records into a fiercely protected, invaluable resource? When we use federated learning and advanced cryptography to reclaim absolute sovereignty over our own identities, privacy is no longer just a roadblock or a hurdle. It becomes the very foundation of trust that allows us to safely unlock the next great medical revolution. Thank you so much for joining me on this explainer. I really hope this changes how you view the future of your own medical data. Keep questioning, keep learning, and we'll see you next time.